Thank you very much, Hamanaka-san, for arranging this online workshop around topological solitons. I've been asked to talk about the construction of monopoles with up to half of the time being a review for beginners and graduate students. Now, the subject's almost 50 years old, and I'm going to spend somewhat longer on the review than this, with only a short part devoted to new results at the end. And my graduate student, Lyndon Disney Hogg, will discuss some of those new results at more length in a following talk. So I know that there are experts there. You may well wish to leave, but equally, I'm going to be referring to your work, and you may wish to be present just to see that I don't damage your reputations. Okay, so to give an overview of such a period of research, I'm going to begin with a timeline with a number of constructions that appeared in the 1970s. These are going to be the ones I'm going to focus on in the talk. So the timeline, I'm going to introduce three types of idea, and I'm going to unpack them as the talk proceeds, and you're not expected necessarily to know what each is. And so after the timeline, I'll give you the actual equations, and I'm going to focus on two constructions due to Nahm and Hitchen, and that's going to introduce the key ingredient in my story, a spectral curve. And then in the second part, my aim will be to show how integrability techniques enable the reconstruction of the gauge and Higgs fields of the monopole. And then we're going to be left with a question, how do we construct such curves? And in the new results part, I'll mention some of that. So here is a timeline. It isn't meant to be comprehensive, but I'm wanting to show how three sets of ideas came together. They're color-coded. Red is to do with monopoles. Blue is to do with instantons. Olive is to do with some ideas that became relevant for both. And then the sole entry in orange is when Baker-Akiza functions were introduced or abstracted by Igor Krycheva. So there were clearly lots of other important ideas going on in the 70s. Supersymmetry was introduced, and in the late 60s and early 70s, finite gap integration came to the fore. Now, those are also in part related to the story, but I'm not going to focus on those at all today. So monopoles and instantons are going to be the main focus, and then integrability. So you can see at the top that monopoles were introduced within a month in two papers by Tuft and Polyakov, and that taught us that topological configurations of field theory were important. In studying the equations that came from those, Prasad and Sommerfeld discovered a solution that was a limit, and that's going to be important to us. And Bogomolny a little later gave us an understanding of why those equations appeared. But once topological configurations were known to be important, we then had quite a number of them, and we had the introduction in 1975 of instantons. In work that came from the Twister group that was at Oxford, Richard Ward showed us how you could relate self-dual gauge fields to holomorphic vector bundles on projective twistor space. And we'll come back to some of this, but that was a separate idea. at that time. And really, I'd highlight the two works in olive there by Severo and Lowe, who showed that we could understand the equations for this limit, this now BPS limit of monopoles as coming from the self-dual gauge fields. That would ultimately prove a very important connection, because it would mean that the self-dual, the instanton techniques could be used in the study of monopoles. But before that, there was a fantastic paper of Nick Manton as a second-year graduate student, who showed that there was no force between two equally charged BPS monopoles. And that would lead to the conjecture that there were stable multi-monopole configurations, and the hunt then was on to find them. Let's see. Well, after Richard introduced this connection, Atiyah and Ward gave an algebrogeometric construction of instantons, which is the AK ansatz. K there is the charge of the instanton. Throughout this talk, I'm going to have charge n, so I'll refer to it as the AN ansatz. So the twistor theory was developed, but the next really big result was by Atiyah and Hitchen, and simultaneously Drinfeld and Manon, which showed that we could construct instantons algebraically. I'll show you that again, but you've had that reviewed for you by Paul Sutcliffe a few weeks ago. Now, using this idea of monopoles being able to be constructed from time-independent reductions of the self-dual equations, Richard Ward used that in the twistorial constructions. He picked that idea up from a paper of Nick Manton, and a number of works cited there that I'll come back to led to the ultimate construction of multi-monopole solutions. Werner Nahm gave a modification of the ADHM construction, and although he had the idea in 1980, it took until about September of 1981 for his famous unpublished CERN preprint with his now eponymous equations to appear. And the last paper that I've got in that timeline is Hitchen's construction of monopoles, and that brings them together. So let me just have a short review of some of the equations. So Tuft and Polyakov introduced, studied the George I. Glashow model, where I've got an adjoint scalar here with a phi to the fourth potential. And they showed that there were topological solutions that corresponded to the expectation of mod phi squared being 1 at infinity. Now, as you saw in Paul's talk earlier on, hedgehog solutions for charge 1 could be constructed, and that's what Prasad and Sommerfeld found. And I've just written down the analog of what Paul gave a few weeks ago. Bogomolny's part to this was he showed how energy bounds could be obtained by completing the square. So he studied quite a number of theories, domain walls, vortices, and included magnetic monopoles. And you'll see here that we can bound the energy by that surface term if we have a set of first order equations. So these are the equations, the BPS limit of the monopole equations that we're going to study. So this is the limit where the coupling constant, if you wish, lambda goes to 0, but we keep the boundary conditions on the field phi, the Higgs, at infinity. And as I pointed out, as I mentioned, Severo and Lowe observed that if you let the fields be independent of time, then the self-duality equations reduced to these BPS equations. Now, just as an aside, although it's less than 50 years ago, the story of where that idea originated is rather hard to determine. Severo's paper is unpublished, and if you go to the Keck library, which normally I find to be very helpful, it will tell you this publication is not inputted. Please come and look at the library. When you contact the librarians, that preprint has been lost. Equally, Severo has retired and has no copy of it. Neither does the Lyman Laboratory, where it was written, have a copy. So there is this paper that I sadly can't get a copy of. And Max Lowe's paper equally had the idea. So Nick refers to both of these papers at various times. Now, Max Lowe's paper has also a puzzling history. I've contacted Max. It has a 1976 preprint date, but really it never appeared until 77, and he can't actually remember the history of it. He can only so how that idea I'm just emphasizing is actually important, and it tends just to be taken for granted. What are the equations that we have? Well, we have that the self-duality equations I've written out here just for concreteness, and I show you that they can be written as a zero curvature condition. And at this stage, psi is just a spectral parameter used to separate the equations. It has no geometric significance, though we'll see such in due course. The monopole equations similarly can be written as a zero curvature equation. And this equation here that I'm identifying with the cursor will be one that we'll come back to. And the conditions that I've said that we retain in the BPS limit, I've just written down here, and N will be the charge of the monopole. Now, the world has changed, and this was of an age when people wanted to solve equations explicitly. The N equals 1 monopole was written down, and the question is, can we find solutions of these equations? So, although Atiyah and Ward introduced the AN ansatz for constructing instantons, the big advance was with what we now think of as the ADHM construction, where we can write down algebraically solutions for n instantons. So I'm writing this for SU2, and this is what Paul told us about. So we write down some matrices with quaternionic entries. We solve an equation, delta dagger V being 0, find the solutions or normalize the solutions, and then we can reconstruct the gauge field as V dagger dV. For this to give an instanton, we require that delta dagger delta be real. That means that this commutes with the quaternions. It has to be invertible, and the dimension of the kernel of delta dagger has to be 1, the quaternionic dimension. So Paul reviewed that in his talk, and Werner Nam's generalization or modification of that to construct the monopole solutions was to change this from being matrices to an ordinary differential equation that I've written down here. So at this stage now, the TIs are complex matrices, and for delta dagger delta to be real, you discover that you require what are now known as Nam's equations, and the first of this equation in N3, this hermiticity property. For quaternionic linearity, this second constraint arises. And then this equation that I've identified as N2 comes from requiring that the dimension of the kernel of delta dagger is 1. So this was Nam's modification of the ADHM data. How do we go from that to construct a monopole? Well, we have this equation. It's an ODE. We look for its solutions. The normalizability then becomes I integrate over the interval. So the interval here is 0, 2 or minus 1, 1. I'm doing this for a general interval because this construction works for monopoles other than just the SU2 monopoles we're talking about. We normalize, we get the normalized solutions, and then we discover, then we can write down in the analog of V dagger dV, the gauge and the Higgs field. Now, here we have to solve an ODE and integrate. And integration is hard, and you might worry that this is impossible. But there was a nice result from the 80s that showed how we could integrate these in closed form. So I've just written this down here. Remember, I've got delta dagger V equals 0. In general, that's got a large number of unnormalized solutions and just 2 normalizable solutions. These indefinite integrals are written for any solution, and then you would need to project appropriately to get at the endpoints to get the normalizable solutions. That is actually an algebraic procedure that I'll come back to. But this slide is just meant to indicate, and we'll use it later, is that the integration can be done explicitly, and really things just depend on the boundary values and their derivatives of either the Nam data or these solutions to the differential equation delta dagger V. So that enables us to construct the gauge and Higgs fields from solutions to this equation delta dagger V. Now, I'd like to just so that's the Nam construction. What's going to be important in due course for us is that the Nam equations take Lax form, and I've written this down here. The alpha and the beta in this construction are related, built out of the Nam matrices, and you discover that Nam's equations are the equivalent of the Lax equations. And these Lax equations can be broken into a pair. These have an interpretation as a moment map equation, and the first of these is a complex moment map, and the second the real moment map. And we saw the first of these in Terashima-san's talk on Monday. They're easy to solve. We can solve these in terms of the eigenvectors of the matrix beta, and in which case we can write down what alpha and beta are in terms of the matrix of eigenvectors. Let me define a quantity H here, G dagger G. It's going to be important for us a little later. So the real moment map, so it's quite general that when we have complex and real moment map equations, the complex one is the easier to solve, and then you're left with this real one. That's true if you study Hitchin systems as well. The real one takes the form, or can be written in terms of this differential equation here, which I refer to as a non-abelian, possibly non-abelian Toda equation. The Toda equations can be written in this form. Donaldson proved the existence of solutions to this equation, this real equation for NAM data. So that what I'm just wanting to indicate is that the NAM data is equivalent to a lax pair, and we're going to come back to that. Associated with a lax pair is a spectral curve. I've used zeta here as a parameter. I'm going to have the curve. To say it's in TP1 is I can't do that just yet. Eta and zeta are just complex variables. And throughout, I'm going to define my spectral curve in terms of a polynomial in eta and zeta. Now, this curve has structure to it from the hermiticity properties of the NAM matrices. You discover that this involution on zeta and eta holds, and we say that the curve has real structure. And I'll just mention in passing that the genus of this curve grows quadratically with the charge n, so it rapidly becomes quite complicated. Now, the connection with twistor theory and mini-twistor theory goes as follows. Ward told us how to write down the solutions of the self-duality equations in terms of holomorphic vector bundles on the twistor space for 4 dimensions, and that's what constitutes the Ward correspondence. There are various technical details that you require on the vector bundles over twistor space. This remark of Severo and Lowe that you could get the BPS equations by a reduction of time independence has an analogous expression in terms of quotienting twistor space by a nowhere vanishing holomorphic vector field. And we can have the construction of our Bogomolny equations at this level, and Hitchin focused on that. Now, let me just tell you, mini-twistor space is the space of oriented lines in 3 space. So a line has a direction, that's our zeta, it's a point on P1, the 2-sphere, that's our direction, and then it's got a tangent direction, eta. And so eta and zeta are going to be the coordinates that you see throughout, and they're coordinates of mini-twistor space. The involution we just saw on the previous transparency is an anti-holomorphic involution, and it has the natural interpretation. It's just reversing the direction or the orientation of the lines. So if we take the Ward correspondence for R4 and we reduce, we get a theorem of Hitchin from 1982 that solutions of the BPS equations are equivalent to solutions in terms of a vector bundle, a holomorphic vector bundle on TP1. I've written here the technical conditions that are required, and I'm just going to, in a moment, make use of one of these, but the same technical conditions that appear to use the twistor, the Ward correspondence, have their analog in this setting. And as we proceed, I'm just going to introduce a notation. I'm going to say L lambda is a line bundle on TP1 with the transition function I've written, and L lambda M is going to be the tensor product of that line bundle with the pullback of OM, where OM is the natural line bundle on TP1. In passing, I would note that mini twistor space also can be viewed as a weighted projective space P112, and that might be important in Lyndon's talk. And for those of you who are very interested in Hitchin systems, you'll see that his later reduction of the self-dual Yang-Mills equations on a Riemann surface followed this line and become a lot easier, and the monopole setting is a lot easier to understand. Okay, so what is the vector bundle E that Hitchin is going to use? Well, remember I told you that we could express the BPS equations in terms of a zero curvature. And if I just let zeta equal 0 in the expression I gave you earlier, it tells you that this operator, the derivative in the 3 direction minus I phi, behaves holomorphically. So the equation I'm going to have, and by choosing zeta equals 0, I've chosen a particular plane, and 3 is the perpendicular direction to it. So fixing zeta fixes a direction. So we can change that to asking about this differential equation here. For any oriented line, let me consider the rank 2 vector bundle given by where you will be a 2 vector, and I'm looking at solutions to this equation. This is a first order equation, and we know that first order equations will have blow up in one direction and decay in another. And I'm going to ask, what is the union of those lines where I have decay in both directions? That is a surface, and I'm identifying it here with the previous spectral curve that we saw coming from the NAM construction from our lax pair. And that requires a proof. And I'd just like to point out Sergei Cherkis has a nice paper, A Journey Between Two Curves, which tells you how such identifications can be made in other settings. Now, at this stage, what have we got? Hitchin's given us this rank 2 vector bundle E. I can have solutions that decay in one direction, and that will give me a line bundle that is a sub-bundle. And then we have a splitting. And the piece that I'm just using in here that actually I won't need later is that with the symplectic structure, we can identify this L minus, the space where the lines decay, with the dual of L plus. But what we have here is an extension problem. And I'm just writing down here the transition function that we have. So we'll have a we'll have a piece that corresponds to L plus. We can see that down here we've got pieces that decay in the other way, and then gamma here is describing the transition. Now, this is precisely the setting that the Atiyah Ward AN ansatz gave us. And Corrigan and Goddard looked at this extension. And so I've written down here one way you can write down what this extension is. And Corrigan and Goddard investigated this and gave a number of constraints that we'll see in a different form on the next page. I would observe that the denominator of this is the polynomial that defines the spectral curve. So this is describing a bundle over TP1. On the curve, this vanishes. So for this to be well defined, the numerator itself has to vanish on the curve. And as I'll show on the next page, this can be understood as that the bundle L2 is trivial. L2 being trivial will tell us that there's a nowhere vanishing holomorphic section. The third, so C has a real structure that's manifest because I've said that it corresponds to the lines where I've got decay in both directions, and the holomorphic involution just interchanged those two lines. So the real structure's apparent. The triviality of L2 comes from examining, as Corrigan and Goddard did, this transition function. And what Hitchin showed was that the regularity conditions could be encoded in this H3. H3 is a little harder to explain. By tensor, we can see that this gives us that the line bundle LS has no sections in 0.2. So Hitchin's wonderful paper that's now 40 years old told us that we had this equivalence of Euclidean monopoles, NARM data, and Hitchin data. And what I want to do is to show how from the curve that underlies each of these, we can recover the gauge conditions. But before I do that, I want to just unpack a bit more about that triviality of L2 over C. So I've said that it means that I have a section, and that section, so if I split my two-sphere into northern and southern hemispheres and then lift that to TP1, I've got two patches, and these patches are related by this transition function. If I take the logarithmic derivative of this, we see that the exponential, because this is closed, will vanish on any one cycle. And what we do is we associate with this section a meromorphic one form. So throughout, I'm going to have this meromorphic one form gamma infinity. It's going to be meromorphic because at infinity there's an eta. It's going to behave like the derivative of eta over zeta, and that's got a pole. I'm going to normalize this meromorphic differential so it's got 0 A periods. So at this stage, I'm going to just use a bit of Riemann surface machinery. So I'm going to just identify the holomorphic differentials on my Riemann surface in terms of these omegas, and Tor here is the period matrix of the Riemann surface. With any integrable system in lax form, when we look at the look at the algebrogeometric solutions, we're going to get a flow, and the flow is related by winding vectors of meromorphic differentials, and it takes the form here. It takes this form. This comes from requiring that the integral around any one cycle is going to be well defined. So Ercolani and Seiner in the late 90s unpacked what this triviality meant. And so we have the triviality, as we've just seen, of L2 being trivial will be equivalent to this expression here being in the period lattice. So this vector U. So U is taking values in the Jacobian of the curve, which is the quotient of C to the genus of the curve by a lattice, which I've denoted here by lambda. And Houghton, Manton, and Ramau gave a dual form of these in terms of a vector, a cycle that I'll call the Ercolani-Seiner vector on the curve, which has the conditions. So this just comes from applying the Riemann bilinear relations to the Ercolani-Seiner constraints. What's important for us is that the Ercolani-Seiner constraints impose G transcendental constraints on the curve. Now, Corrigan and Goddard got these constraints, and when you take those constraints into account, you get the right dimension of the moduli space for a charge n instanton, and what charge n monopole. And what Hitchen showed is actually that the AN ansatz gave you all of the non-singular. Now, it gave us all of the spectral curves and would reconstruct all of the monopoles. Well, I've said transcendental constraints. You can actually make that more specific, and you can argue that or more concrete, you can make that you can argue that the BPS monopoles are transcendental in the ordinary sense that you might think. That is, they're not going to be defined over the algebraic closure of the rationals. So if you look at these equations, which are until this year all of the known spectral curves, there'll always be a coefficient hidden in here that's transcendental. And Linden, in his talk, is going to give two further classes of curve that I'll show you briefly toward the end. So I just observed that many people have found these. Prasad and Sommerfeld, Prasad and Rossi had found the axially symmetric charge n monopole, and Hitchen has written down their spectral curve. Hurtubise did the charge 2 monopole. Hitchen, Manton, and Murray looked at a number of curves with Platonic solids, with Platonic symmetry. So Platonic symmetries just bring joy to your heart, and they have shown how to get spectral curves and monopoles with those symmetries. And then Houghton and Sutcliffe gave a large number of monopoles with other symmetries. All of these give quotients. All of these, apart from the last, and the first three, will give quotients to an elliptic curve. This last one gives a class of charge 3 monopoles with cyclic symmetry, and it's a genus 2 curve. the Hitchin, Manton, Murray, when they examined the Platonic solid, could rule out, for example, icosahedrally symmetric charge 6 monopoles. I'm going to come back to this idea of using symmetry to simplify obtaining spectral curves. But I would note that, disappointingly, after 40 years, these are, together with the two that you'll see a little later, the only spectral curves that we can write down explicitly. Okay, so far we've focused on the curve. What do the fields look like? So I'm just giving you here what happens with the cyclically symmetric monopoles that I had described at the end. So here I'll work backwards. I've got 3 monopoles relatively well separated on the vertices of an equilateral triangle. As they come together, they go through the tetrahedrally symmetric monopole, and when they come out the other side, you'll get a charge 1 monopole and a charge 2 monopole, or that are well separated. Well, what can we say about the fields? I haven't had time to tell you about rational maps. There are 2 rational maps that we can associate with monopoles, the Donaldson rational map and the Jarvis rational map. Because of time, I won't describe those in more detail. How do we reconstruct the fields? Well, we can do that numerically. And Paul Sutcliffe, who's online, has developed many numerical techniques for reconstructing monopoles, both from NARM data and rational map data. And you can get the pictures that he has, the analogous pictures to those that he showed us the other day. I'm going to be more interested in analytical solutions. So for charge 1, we've written the hedgehog. For charge 2, Prasad and Rossi did it. For axially symmetric, higher charge axially symmetric monopoles, Prasad and Rossi did it. For n equals 2, even before 2019, only parts of the space could be treated analytically. And what I'm going to show you is the way that you can do all of R3. And that was work with, so the field configuration on all of R3, and that was work I did with Victor Anolsky. So my aim is to show you how to use integrability to solve for the fields. And there's a general structure here that I'll alert you to. So we have equations. For us, the BPS equations. We express them in zero curvature form, and we get a curve. The function theory of that curve enables you to reconstruct the equations. Now, clearly, there's lots of machinery in here, and I'm not wanting to take you through all of the fine details of that. The functions on a curve can be written in terms of theta functions. And everything I tell you, I can write quite explicitly. And indeed, I've got a number of new and rather explicit formulae. But I think it would be cruel. Yeah. So to avoid undue cruelty, I'm not going to expose you to the actual formulae. I'll tell you schematically what happens. Alfors some time ago wrote that theta functions are still from being a spectator sport, and I think that quote is as true today as it ever was. Now, I've done something here that I should say isn't obvious, and it's not necessarily true. What you want to do, and what happens in the monopole setting, is that the nonlinear equations that we have over here, we ideally would like to be able to relate to a straight line flow on this torus, this Jacobian. straight lines are the nicest things that we can deal with. That's not necessarily true, even with a lax pair. There's a cohomological condition that Griffiths highlighted, and it is true in the NARM setting. There will be integrable systems for which it's not true. But what it means for us is that everything can be written in terms of linear flows. The direction of the linear flow we've already encountered. It was that winding vector u, and all of the complicated expressions I've given in terms of cohomological data have analogous expressions in terms of straightforward expressions in terms of the theta functions. So there being no sections tells us that the theta function is non-zero. And because the fields are expressed in terms of combinations of these theta functions rational, we don't want the theta function to be able to vanish apart from the endpoints. So what I'm going to do is I'm going to solve the ADHM data using integrability. And what you discover is that we're not going to need to make a gauge choice. And there's only ever, when you write down the fields, there'll only ever be one transcendent quantity. Everything will be in terms of the space-time coordinates, apart from some combinations of the integrals of this gamma infinity. So our approach, I've told you, and I'm just reminding you here, is we wish to solve delta dagger V. I'll combine that into a matrix of the fundamental solutions. We wish to get the normalizable solutions, but we have a problem. If I just give you the curve, you don't yet know what the t's are, so you don't know how to construct delta dagger, and hence, how do we solve delta dagger V equals 0? Now, here we come to another that I refer to as a lesser known ansatz of NARM. NARM actually tells us how to solve the equation delta W equals 0. I'm using the benefit of some hindsight to write this in a simpler form, but NARM also came to this from twistor theory. So Y here is a complex vector in C3 that's null. From that, you can construct an orthonormal basis of R3 in terms of its real and imaginary parts and this vector U hat. I'm just going to pull out of the air a vector of this form. So U hat is this direction I've told you about, and chi here is some normalizable spinor that's not in the kernel of this operator here. So I put in delta W, and I discover it breaks up into the lax equations that we've seen. This identifies eta, the eigenvector with the space-time point with the space-time point x in this fashion, and NARM's equations have to be solved. So this gives us our approach. I can take a space-time point x, I can put it in into my curve here. That's an equation of degree 2n in zeta. That's going to give us 2n points on the curve, and then I can form a 2n by 2n matrix, W, built in this fashion. So we're done if we can solve this lax equation here. And the way we can do that is using this Baker-Akiza function. So I've written there the general definition of a Baker-Akiza function. It's an extension of meromorphic functions on a curve to allow essential singularities. I call those punctures. And for us, that's going to be the points above infinity where eta over zeta where eta over zeta, where the exponential of eta over zeta is a singularity. So, see that. Recall we had the Lax equation. How do I get this Baker-Akiza function? Well, it's going to be coming from a solution of the scattering equation. But it's got to be a standard. We have to be able to solve the equation in a standard form, right? I'm wanting a singularity that goes like a constant by eta over zeta above these punctures. Now, the problem with the matrix M is that it's got coefficients that are of zeta that are S dependent. So this is not a standard scattering equation, but we can gauge it, and indeed we've seen the right object to gauge it with, that the eigenvectors of beta that we saw earlier, if we make that gauge transform, our equation here goes to the standard scattering form, and I can recover the Baker-Akiza function. From the Baker-Akiza function, it's then possible to recover the gauge transform of the Lax matrix, the gauge transform of the NARM data, and in fact, as Victor and I showed, we can get H in this explicitly. So we haven't got the T's, so we haven't really got got delta. To solve for the T's, we would need to solve that matrix factorization. But what I show is that actually we don't need to do that to reconstruct the fields. We can reconstruct the fields by just, if we put in what that gauge transform is, one discovers the objects that I introduced very early on in the NARM construction. It turns out that the only combinations of this gauge transform are either in the form of H, G dagger G, or in terms of the coefficients that I get of this transformed, this gauge transformed Lax matrix that I can read off from the Baker-Akiza function. So what this is just showing is that, and this makes physical sense because you have to choose a gauge. We can write down the fields explicitly, and we can then construct things like the energy density and so forth without ever having to specify what that gauge was. Let me just make a couple of quick remarks. To finish the story off, you have to be able to get the normalizable solutions, and you can do that. There are a number of nice that follow. I'd also like to observe that if the spectral curve has symmetry, then you can quotient by some subgroup of the automorphisms of that curve. You get another Riemann surface, C dash. The Jacobian of this this reduced Riemann surface appears, and there's some residue, some abelian variety that I'm not going to focus on here. So the best of all possible worlds is when this vector that appeared in the Houghton-Manton-Ramal description of the Ercolani-Steiner constraints is G invariant. You can actually reduce everything to this smaller curve, and in that setting, solve for that. And this actually happens in a number of examples. In particular, the cyclically symmetric monopoles are reduced from something of genus n-1 squared to the Toda equations. Those might well appear in Lyndon's talk. And one discovers that an ansatz that Paul Sutcliffe gave many years ago for cyclically symmetric monopoles are actually obtained on the nose from the affine Toda equations. In the last few minutes, let me just give 3 more slides. What about new results? Here I've indicated all of the known charge 3 monopole spectral curves. Everything in this lower part will quotient by a symmetry to a elliptic curve, and this was the cyclically symmetric genus 2 curve. This quotients to a genus 2 curve under the cyclic symmetry related to the Toda equations. So they're all related. So this is the tetrahedrally symmetric monopole of Hitchin, Manton, and Murray. This will be one of the C4 symmetric. This will be the C4 symmetric class of monopoles that Houghton and Sutcliffe gave, and these are others that we've seen. This curve up here will correspond to a new class of monopoles that weren't thought to exist, and down here I've got some V4 symmetric monopoles. Sadly, I'd thought that this was totally new, but it turns out that in Houghton's 97 thesis, curves of this form were considered, but Connor there only solved for a particular restricted subset. And what Lyndon and I have done is we've solved for the general monopoles in this class. Because time is running out, let me just give you what the energy density of those V4 symmetric monopoles is. Now, if we were in person, which I would like to have been, I have a 3D printing of one of these. And it's a nice exercise, if I give it to you, for you to pick out what the V4 symmetry is. It's not the C4 symmetry, and anyway, it's a lovely new object that I'll let Lyndon describe. So let me just conclude. I've reviewed the Nahm and Hitchin constructions of monopoles and given their associated spectral curve. For me, the spectral curve is the critical thing. I've shown how you can reconstruct the fields from that. I've indicated very briefly how you can use symmetry to reduce the curve and the problem that you have. The known charge 3 monopoles that quotient to an elliptic curve were given on that previous slide, and in there were 2 new families. Lyndon will describe, as I've run out of time, how to solve the transcendental constraints. Why have I reduced to genus 1? Well, if what I've told you is that you can reduce, and you reduce the Ercolani signer vector, when you get to genus 1, there is just one transcendental constraint to solve, and that's a more manageable task, and that's why we've chosen this class to focus on. So I'll leave you with the challenge, how to find monopole spectral curves. So although the subject is some 50 years old, the number of monopole spectral curves that we can explicitly write down is rather few. Thank you for your patience. And I see that there's already a question, so over to you.
Okay, thank you very much for the comprehensive discussions.